Okay, thank you. Okay, so what is the paper about? So the main question has been, a central question in economics, at least since Hayek. So do financial markets aggregate information through prices? Suppose that we're trading an option, a derivative on an underlying asset of a company, and the traders have different private information. So I may know whether the CEO is of good quality. Another trader may know whether the new product is going to be a success or not. So if we're able to come together and truthfully reveal our information, then we would know the true value of this asset. The question is whether the market, through the changes of prices, can actually reveal the true value of the asset. So when I buy a security, I buy, let's say, the option, I reveal to everyone else that I have some good information about the asset. So this information, everybody else gets it, updates their beliefs, and then they trade. They can either buy or sell. So then their action is going to reveal some information to everybody else. So as the price goes up or down, the good scenario is that all the information is going to be revealed. So eventually the price is going to convert to the true value of the security. Okay, the security is essentially a function from states to outcomes, like a stock or an option. So the question is whether this is happening and under what conditions. Ostrovsky has a very nice paper which says that there are these securities which are called separable, and separable securities always aggregate information in all NAS equilibria as long as agents trade for a long time. So this does not depend on how many traders you have, whether you have a monopoly or you have many traders, perfect competition, doesn't depend on the market power. So it's a very powerful result which shows that markets are efficient. However, separability is a function, is a property of information structure. By information structure, I mean the initial private information that every trader has. So if I'm the market designer and I know what is the, let's say, the partition of the information structure of the traders, I can understand whether the security is separable, and therefore I can understand whether in all equilibria it's going to aggregate information. However, in most cases, I do not really know who trades, and therefore I do not really know whether the security is actually separable or not. Okay, so now what this paper does is we're asking whether this problem of this robustness of separability can be solved by the availability of cheap information. So we live in a time where it's very easy to access a lot of information, and it is very cheap to access it and process it. So what happens if in a market, as we trade, we can also acquire extra signals about information? So what will this possibility make everything separable? So essentially what we do is that we enhance the model of Ostrovsky by allowing traders to acquire signals in every period, costly signals. So what are a preview of our results? So without information acquisition, so if we go back to Ostrovsky, very few securities are separable for all information structures, and we characterize them. Then we generalize the notion of separability, what we call kappa separability, where kappa is the cost structure of the information signals. And then we characterize information aggregation with respect to kappa separability when the cost structure is kappa for signals. And then we ask the question, okay, what happens if the marginal cost of information goes down to zero? So what happens then? So obviously everything becomes, you can buy a lot of information. Does it mean that everything becomes separable in the end? We saw that surprisingly, this is not true. There's a discontinuity at the end. So there's going to be some very few securities that we characterize that will never become kappa separable, even if the marginal cost goes to zero. Converges to zero, but it's not exactly equal to zero. And then the last result, if I have time, if you have information acquisition, does it mean that information aggregation is going to become faster or slower? We saw that in all cases, it can be both faster and slower unless the securities are the blue, in which case, in a myopic setting, the speed of aggregation does not change. Okay, so we model trading using market scoring rules by Hanson. This is a very nice model because the issue of information aggregation is the only thing that matters in that model. This is also used by Ostrovsky. There's another more famous model by Kyle, but there the issue of information aggregation, the issue of information revelation, they are sort of intertwined. Ostrovsky uses both models, and also prediction markets uses market scoring rules, and also market scoring rules can be reinterpreted as an automated market maker that are used in trading on the blockchain. So actually prediction markets and market scoring rules have a practical significance as well. Okay, so this is the related literature. So obviously a lot of these things stem from the no-trade theorems, Oman and Milgram and Stockey, the market scoring rules by Hanson, and separability and information aggregation by Ostrovsky, and then rational attention is about costly information signals like Matejka and McKay and Kaplan. Okay, so I'm going to tell you a little bit about the model. So we have a finite state space, finitely many traders. We have a security X, which is a function from states to outcomes. You can think of an option or a stock of a company. You have asymmetric information. So my information initially is a partition of the state space. So a state happens, and then I consider some states to be possible. This is my private information. And the sequence of plays that essentially there's sequential trading. So a market maker makes an initial announcement Y0. In period T1, player 1 makes a new announcement about the value of the security. And before announcing, each player can buy a signal. And I'm going to say what this is. There are infinitely many periods, and we say that information gets aggregated if the sequence of announcements converges in probability to random variable X. So for every state omega, X of omega is the true value of the security. The question is whether the Y's are going to converge to X of omega for all omega. That's if this happens, we say that this is this information aggregation. The payoff, the trader's payoff, so this is the market scoring rule. S is essentially the score of announcing YT at period T. X star is the true value of the security, which is going to be revealed at the end of the trading. And then you get your score minus the score of the previous announcement, the YT minus 1. It's called a strictly proper scoring rule. If whenever I'm myopic, if I only care about today, I will always announce my true expected value of the security. So essentially, this is the same thing as saying that the scoring rule when you announce probabilities. If it is a proper scoring rule, you would announce your true probability.
May I ask, how should I think about this? What does announcing YT mean? Is it like I'm trading YT shares? And if I'm trading YT shares, why does my payoff depend on how many shares my predecessor trades?
No, YT is essentially the value, the price of the security. So if the current price is 2.
Am I buying or am I selling?
Yeah, so if it's 2 and then essentially you announce 2.5, essentially you're buying the security because the previous one was 2, so you're increasing the price to 2.5.
I see. So it's the whatever. It's
the price,
the
yes.
limit order or whatever.
Yeah. So this is the price, and and you get the payoffs at the end. Yeah. So now this is the definition of separability by Ostrovsky. So we know from Oman and Milgram and Stockey and Giannakopoulos Polemarchaki, which says that if we trade for a long time, we can never eventually we'll agree on the price of the security, right? That's the no-trade theorem. So separability says the following: so a security is non-separable if I can find the prior such that everyone agrees on the price of the security. This is going to happen at the end, we know from Giannakopoulos and Polemarchakis, but at the same time, the prior has support on states such that the price of the security can be different, right? So although we agree on the price, there's uncertainty about the security. This means that there is no essential information aggregation. Otherwise, if we can never find such a prior, it's going to be called separable. So the prior mu here is essentially the prior that an outside observer is going to update after hearing all of the announcements and incorporating all of the public information by all the buy and the sell orders. Okay, so as I said before, separable securities aggregate information in all equilibria, but separability is not robust to changes in the information structure. And now this is our first result. So we want to characterize the securities that are always separable. So securities that for all information structures, they're separable. And there are only three of them. So one is the constant, which is very uninformative and boring. The second one is the hour de Brue. It pays $1 at one state and zero otherwise. And the third one has only three states. It has a minimum value at one state, the maximum value at another state, and in all other states, it has a constant value. So these are the only securities that will aggregate information for all, for all information structures. Okay, so now we go to information acquisition. Suppose that traders can buy signals in every period. So what is a signal is a function from states to probability distributions over signal realizations, and then you have a cost H of the experiment, the statistical experiment R, that may or may not depend on your prior mu. We don't really make any assumption about these signals. For some of our results, we require that it's not possible to buy a perfectly informative signal that will reveal with probability 1 the true state. Because in that case, it would be very trivial to see what's happening. So CK is essentially, C is the marginal cost of information. So K is the cost of moving your prior mu to a random posterior, which is essentially a probability distribution over the posterior that you're going to have from the different signals. Okay, so now how do we generalize separability? So as we said, the security is not separable if I can find the mu such that everyone agrees on the price, but there's uncertainty about the value of X. So according to Giannakopoulos and Polemarchakis, this would terminate trade because there will not be any reason to trade more. Okay, so what happens now if we want to talk about kappa separability, kappa non-separability? If this is true, if additionally we agree on the security of the process security, but at the same time, nobody is willing to buy any new signals. So there's no appetite for acquiring information. So if that's true, then we say that the security is kappa non. Okay, so just to give you the results. So the first one is the generalization of Ostrowski. So we fix information structure in a cost structure kappa. Then if security X is kappa separable under this pi, then in any NAS equilibrium, information gets aggregated. Conversely, if it is kappa non-separable, then I can find an equilibrium, a perfect Bayesian equilibrium where information does not get aggregated. So kappa separability characterizes information aggregation. The second theorem says that, okay, so suppose that we can decrease the marginal cost of information and convert it to zero. So what happens in terms of kappa separability? We saw that a security is kappa non-separable given pi and for all kappa, so for all cost structures, if and only if it has the following structure, which is that in at least 4 of the states, it pays A, B, D, D. So where D is one value, and the other 2 states, it can either be on the left or on the right. Of course, you can have many more states, but if I can find 4 states where this pattern is there, then this means that even if the marginal cost goes to 0, I can always find some information structure, some prior, such that there's going to be no information aggregation. Okay, what is the corollary of that? The corollary is that if the security pays differently across all states, then we know that as the marginal cost goes down, then the security is going to become a separable eventually. So if you have a security that pays differently across all states, you don't really need to know who trades, what is the information structure. If you think that the marginal cost of information is going down, then you will know that this is going to be a good security because it's going to eventually aggregate it. Okay, so just to give you some pictures now. So I have 3 minutes or 2. Okay, so these are the 3 cases. So the nice thing with this exercise is that we understand what happens with kappa separability only by looking at the payoff function of the security. Whereas with separability, it's very difficult to understand whether security is separable or not. So the case 1 is X is always separable. So it's a constant, the constant security. The arrow, the blue security, just pays 1 or 0 otherwise. And this is the third security that is always separable for all pi. Just 2 states, maximum and minimum, and constant everywhere else. This is the problematic security. This is security that even if C is very close to 0, you may get the situation of no information aggregation. You have 2 states, at least 2 states that provide the same payoff, and then 2 other states that are either above or below. And this is the nice type of the security. It just provides different payoff at all states. And this is a situation where if C is sufficiently low, the marginal cost of information, then it will always aggregate information for all equilibria and for all information structures. Okay, so this is another, a few more pictures, the same thing. So you have the set of all securities, the separable securities, the always separable is a strict subset. And then as I allow agents now to acquire more information, then I can get more and more kappa separable securities, but there's going to be the wide sort of margin are going to be the securities that are kappa non-separable for all kappa. 1 minute. Okay, so I'm going to skip the speed and just go to the discussion. Okay, so what's the idea of the paper, right? So the main question is, do markets aggregate information? Ostrovsky showed that separable securities aggregate information. However, this property is not robust to changes in who trades and what is the private information. We enhance the model by allowing agents to buy information signals, and we characterize information aggregation with respect to this kappa separability. And then we also provide the complete classification of all securities according to their payoff structure in terms of whether they always aggregate information, whether they do not aggregate information, and whether they aggregate information as long as the cost is actually sufficient. So that's the paper.
Isn't there a Grossman-Stiglitz paradox that would suggest the exact opposite of what you showed us? That basically, if it's costly to acquire information, then and it would be aggregated in the price, then I don't want to acquire information at all. I can just look at the price.
I mean, with Grossman-Stiglitz, there's issues that you already imposed the notion of an equilibrium, right? So what is a price equilibrium? That the prices actually reveal information already, right? So here it's a bit different because here we only impose the Nash equilibrium. We see what happens at the end. Okay. So it is true that in a Nash equilibrium, it could that some people, I mean, first of all, you have some information at the beginning that reveals the true value, right? Now the question is whether I can free write on you revealing some of the information. This can happen in many of the equilibrium files. We can have that as well. The question for us is whether at the end, whether the price is going to be correct or not. So we saw that in all equilibria, this is going to be true, right? But people are endowed with enough information at the beginning to reveal the true price. Whereas maybe in Grossman-Stiglitz, maybe everyone is uninformed. So in principle, it could be that nobody buys information.
See, Stiglitz is just one-shot move, right? In your model, it's sequential move. And I guess the related question is, suppose that we can decide endogenously in terms of who moves first. Let's say Kevin and I arrive at the same time. Does Kevin want to be the first player or he wants to be the second player? I think maybe what he was suggesting is that everyone wants to be the last trader because we want to see what other stupid people are doing before we.
Yeah, that's true. It's an interesting idea because I mean here the order is fixed, right?
Right.
But it would be interesting to see what happens
first.
and also if somebody can actually, because what's happening. I mean, an interesting thing is also in let's say trading on the blockchain. You submit your orders, but then the order in which these orders are going to be satisfied are strategic, right? So that's also another interesting question. If you can change the order, whether the information aggregation is going to be not satisfied.
So you are using the market square, right? So is there like some incentive for people to go earlier so that they can kind of capitalize on, the fact that if they add information first, there's like less information for future traders to add.
Yeah, I mean, you can construct equilibrium like that, right? Where I don't want to buy information because once you move, I can then clear the market because I will know what's happening, right? But in this model, what we care about is what's going to happen in the long term. So what we can show is that in the long term, somebody has to move, and eventually somebody can capture all of the surplus and get the price, right? But there are going to be interesting equilibria where I'm free riding on you, for example, with a final time horizon.